And here, as the other path is from the chisel, you can automatically create a so-called target compiler, which gives you the exec file you can load then into the RTL simulation and also FPGAs on the chip. So this is our basic framework. Yeah. At the university, we are using low-cost FPGA boards. Here you have the example of the RT7 9035T. This gives you a number about the capacity of the FPGA. So each FPGA has different capacities. The capacities are measured by lookup tables or LUTs, L-U-Ts. Yeah. So this is the 635T is a FPGA board with very low capacities, so in the range of 17,000 LUTs. Yeah. The 100T has about 50,000 LUTs. In previous times, before COVID, this board was low cost. Yeah. So we purchased, well, for our labs, we purchased 30 of these boards for our labs. Yeah. And they were at the cost of, how does it compare? 10,000 rupees approximately. Yeah. So, but meanwhile, I checked yesterday at the internet. The prices now got up from 10,000 to 61,000. So I'm not really sure what is really happening. Maybe there's a problem with the AI. I think they mismatched some information there. I had the feeling that Google is talking about these boards. In previous times, it was 300 US dollars. This was 100 US dollars. So this were actually the ideal boards which students can also buy for their home studies. Yeah, in combination. Once you have this board from AMD, then you get the tool for free to run your synthesis steps and to then configure these boards. Here you have a couple of displays, 7-segment displays, some switches, some LEDs. You can then easily play also very simple experiments on this. Yeah. So this is what we are using here. Then here we have used this flow for TSMC, 65 nanometer, yeah, which is a commercial PDK. Basically means if you are not registered on our servers, you have no access to it, yeah, which is a big problem for homework. Either you need our server access, or you cannot do anything. Yeah. Also, this is also the other obstacle, cadence, in combination with this. Yeah, because you need licenses. Yeah. The solution is that IHP, the fab in Germany, now released a PDK, which is open source. You can download it from GitHub. And this is called SG13G2. 13. SG stands for silicon germanium, and the 13 for 130 nanometers. So you can download, you can review everything which you can use this. This flow is our current work. We need to integrate it so that students can use it at home. Yeah, so that you don't need any server access once the problem with the cadence is resolved. There we also are working on a solution. So these are the commercial problems here. On this flow, This is easily solvable by low-budget hardware. Yeah. This is the RTL simulation is for free. It's an open source software from the Chipyard framework. Yeah. So, however, there was some mysterious other flow, which was called FireSim. We were not really familiar with, and we didn't know what it is. Yeah. Because there were some descriptions, there were some publications, some contradiction. What is done here is they put the RTL simulator on a FPGA, yeah, so that it becomes accelerated, yeah. So they called it accelerated RTL simulation, and it's FireSim. So main problem is. I will now focus here on this part, yeah, and a comparison what is happening here. So we made some first tests, yeah, and then so the system Verilog which was generated was over 100,000 LUTs. So it exceeded also the 100T FPGA. So we couldn't use it. So, but this was not the end of the story. I received some help from Paderborn University. If we cannot solve it in the small, we can solve it in the large. So we have a high-performance computer center called Paderborn Center of Computing, and they have a cluster. And they have bigger boards, FPGA boards, with a size of 1.3 million LUTs, rather than just 17,000. Yeah. So then we tried to use this. And then the question was, once we are using this, why not also try to speed up the varilator on a high-performance computer? And there we have very surprising results. Let me first go into this comparison, what we achieved. Here, this is a very short overview of our high-performance computer cluster. It's equipped with 1,126 nodes with AMD high-performance CPUs. And then we have 48 FPGA boards, and each, I already told you that, 1.3 million LUTs. So this is a short characterization of our HPC center. This is why we couldn't use the small ones. Yeah. Bigger ones would have come to the cost of around $10,000. This would be then in the hundred thousands of rupees. So for the next slides, you also need the information what varilator is. Yeah, varilator is, as I already told you, a RTL simulator. It takes Verilog code and compiles it to C++. And then this C++ is then compiled to an executable, and this makes the simulation. So very short information. What you can do is you can have a parameter called threads. So you can then have multi-threaded C++, which gives you a higher performance. This is what we expected, yeah, in the executable. Yeah. So let me show you what we found out. So this is first the results of our high-performance computer. Yeah, with 64 cores. Yeah, what is very important, I will get it back. So if the number of cores, the number of cores need to be greater or equal the number of threads you define here. Yeah, so otherwise the varilator does not start. So we had then a software benchmark we created by ourselves with 100 million instructions, which is pretty large. Yeah, so it's not trivial software we are executing. You typically, when you go into RTL simulation, you only execute 100 instructions or whatever, but this then does not give very good results. What we did is we compiled very later with 1 thread, 2 threads, 4 threads, 8 threads, and 16 threads. Yeah, and then by surprise, with the number of threads, the runtime of the same simulation decreased up to this point, and then it increased again. Yeah, so it almost doubled from 8 to 16 thread. This is against our expectation. Yeah, so this was the first surprise here on the HPC. Yeah, so then we applied the same experiment on a desk computer and a desktop computer, which was a modern 6th generation Intel Core i5 with 16 cores. Yeah, and then we did the same study then, and we checked it with 1 thread, 2 threads, 4 threads, 8 threads, 16 threads. And by surprise, this small desktop was faster than our HPC center. Yeah, yeah. By in our example, by always 40 minutes. Yeah, this was a big surprise. Yeah, we checked then what was the reason why, and our explanation is the frequency. So this desktop is running at 4.6. And this is the HPC is just with a peak frequency of 2.4. Yeah, so this is a good message actually for you. You can download it, and then you have faster simulations compared to a HPC center. So actually, for the very later, you don't need Verilog once you have more cores. Yeah, you can see it here. With just 1 thread, it's double as 4 threads. So what is also the bad news is you have to find out the optimum. So we tried it with other example. It's not really sure how to create the optimum. You have to run it, identify it by experiments. But once you have it, you can then arrive at very fast simulation times. So what is the results? Conclusion: modern desktop computer can be faster than a HPC. Yeah, and this HPC was really powerful. Yeah, yeah. So then the other question was, how fast is the accelerated FireSim? Yeah, so we took the same software. Yeah, also very later with 1 thread, 2 threads, 4 threads, only on our HPC cluster. This was the minimum was at here. And then we arrived at a runtime of the RTL simulation. Most of you probably cannot see it. I'm sorry for this. Yeah, at 1.9 seconds. So this is a speed up of 5,300 times, yeah, which is really, really fast, yeah. So, as you can see here, but this is, you can, even with the other experiments, you can achieve faster speed ups, but here this was the minimum speed up. So this can take you a lot of time in RTL simulation, yeah. However, you need a HPC center or a very big FPGA card. Yeah. Then we made another experiment. So this is the number from the last slide. So then we computed the so-called MIPS. MIPS stands for million instructions per second. This is a typical number to to identify the performance of an execution of a compiled software. And we arrived at here with our RTL simulation at 52 MIPS. These are the number of so-called virtual prototyping environments, of professional prototyping environments. And I can tell you this is very, very, very fast. Yeah. You can also see that we then scaled the software. So we then let the sorting algorithm run not only once, then 5 times, and so that we had a series of measurements, and they were already only what we see here is with at least 50 MIPS or larger. So this was the surprise of our first experiment. Now we wait, and I will go a little bit quicker through it. We then made experiments with UC Irvine, yeah, with Professor Dömer. And I will step a little bit quicker through it. So we then, on the first slide, I showed you the electronic system level design, where we start at system C and then continue with RTL simulation. Yeah, this is a step where you have to transfer the system C model of your hardware and software to the Chisel hardware description language. Yeah, so this is a design issue, and you need a designer for this. This is not automation. Yeah. So, but I will only go through the results of the experiments. I have to skip some parts of it because I did a very long introduction for this. There we measured. So what you can see here on the left side, these are the well-accepted so-called levels of abstractions. Yeah. So you typically, in theory, this is the academic way. Yeah. You start with C++, multiplied threaded C++, then you go to system C, to a standard level called transaction level modeling. Then you go to instruction sets simulation, RTL and FPGA, and Chisel, and so is here. And we did a complete example with non-trivial hardware and non-trivial software. Yeah. For the non-trivial hardware, we took the approach of Professor Dömer. There we designed or implemented in Chisel so-called RISC-V grids. I'll show you a little bit later, which are basically structures like a checkerboard, yeah, where you have then scale these grids to 2 times 2 or 3 times 3 or whatever. And this is what Chisel is ideal for. Yeah. Yeah, you just have one structure, and then you just multiply it by a factor, and then you get a larger circuit. Yeah, this is what we did. So we had here experiments with the different grids: 2 times 2, 4 times 4, which is basically four RISC-V processors. Here we have 16 RISC-V processors, here 25 here, and so on. Yeah. So, and here is the runtime, and because we are talking about different things, here on the instruction set simulation, we are talking about instructions. Yeah. On the RTL simulation, we talk about clock cycles, yeah, which is different, and therefore we had to normalize it. So This is the first study we did, and which I'm aware of, on the only study which then makes comparison. Yeah. So we start of this whole thing over all abstraction levels. Yeah. So we started here at the functional level, and this is here the approximate runtime. So we are here at 10, 100, 1,000, and so on. Yeah. So then we made measurements that verified that with our software example, TLM was 10 times faster. Yeah, 10 times slower. Sorry. Then the next level. Oh. The next level was here the instruction set simulation. At this level, you can run the software only the software with a factor of 100 times faster. And here comes the real bottleneck from here to here. We have the RTL simulation, which is pretty slow. Yeah, and this is our bottleneck we have to solve. And compared from here to here, we have 10,000 and we have 1,000 and 1,000, which makes a million, which basically means one simulated second here makes here 2 weeks of simulation. Yeah, you see the problem here. So we resolved this problem by scaling the software, and we defined special software with different scalabilities, non-trivial software, which basically means that we scaled by the number of communication steps within the RISC-V grid. Yeah, so we scaled down the communication step in order to get acceptable RTL simulations. So, having said this, I now would like to give you some examples in Chisel, because nobody so far has ever seen a Chisel design. A Chisel example is written here. It's based on the scripting language Scalar, which is basically for software implementation. And this is some extensions on it. Here you have classes, yeah, and which extends the modules. Then you have here the inputs and the outputs. And then you simply define the bit width of these inputs and outputs. And then you have such simple statements. So adder is then here input A plus input B. This makes an adder. Yeah, very simple, very scalable, because when you here put 64 in, yeah, then you have a 64-bit adder. Yeah, very simple. I think you can see here now the advantages. So then with the context, Rocket Chip Generator is a tool which generates, as showed you at the beginning, with a tool which generates system Verilog from Chisel. Yeah, and it supports the so-called Rocket Chip SoC, which stands for Systems on a Chip. The system Rocket Chip SoC has currently the Rocket core, or you can alternatively use another RISC-V core. So what is it about? This shows the SoC structure. You have a so-called rocket tile with the rocket core, a page table walker, level 1 caches, and a connection to the buses, which then connect to the other peripherals. I don't want to go into the details here. The chipyard has a special bus system with bus system synthesis, and the bus system is called TileLink. Yeah. Therefore, everything is in TileLink. Here, this is TileLink, this TileLink, this TileLink. So, how to use this? We tried to model the grid of processing cells from Professor Dömer. This is the basic structure, and the basic principle is that we have local processing cells with local memory without any system bus, shared system bus access. Yeah, this is the principle of his architecture, and you only have access to the neighbor memory. So what did we do? We took the basic SoC and replaced the level 1 data cache by a scratch pad. This was pretty easy. Then we removed several parts because we didn't want to use the caching. And then we reduced the AXI buses. Moving things is always very easy. And then you simply had to replicate these modified tiles. Yeah. So this shows you the principle and how easy it is basically. However, it took us one project group over 2 semesters to do this. Yeah. However, you have to consider that the students need to be educated in chisel. Yeah. But I think this was an impressive result. And then we finally arrived at the sizes of the different sizes of the different grids for the different boards here. Yeah. Yeah. So this was only after 2 semesters. Another design example is the Tetrisc. This is a fault-tolerant RISC-V-based system. It was introduced by IHB, Frankfurt Oder, by Dr. Ulbricht. Yeah? And it is basically a multi-core system where you can switch multi-core operation with lockstep operation. Lockstep is basically running many cores in parallel and comparing the result. Comparing the result is a voter, yeah. And if the result is not the same, the voter gives you a warning, and then you can implement some measures, yeah, yeah. What to do, yeah. You can then reboot or whatever you like, yeah. The system they implemented was based on risky Palpissimo SoC, which is a completely different SoC, but also based on RISC-V processors. And the development took them 2.5 years. They taped it out and they had a FPGA implementation on it. Yeah. So they approached us and they asked us to re-implement everything in Chisel. Yeah. So this is now the baseline again with the rocket chip SoC. What we did is then we made some internal modifications in each of the tiles, and then we implemented also a voter and a controller and a register where the software can decide to switch to lockstep mode or back. Yeah. So, but this should be sufficient here for the architecture. This took us 9 months so far. So in contrast to the others, and we already have a FPGA implementation now. Yeah. Provided our chip flow has been implemented yet, we are very close to tape outs then. So let me come to the conclusion. Yeah. Chipyard for education. So how to apply Chipyard for education? And this is our plan. We would like to finish. I told you about FireSim. This is definitely not for education. It's IP, a high performance was on the high performance cluster. This has nothing to do with students at home. Yeah. So At the moment, for the chip design, we are using Cadence, and here this tool is for free for this board. So we are happy for this. So this is our plan to stick with this board and with this flow. Then you can get from Chisel to RTL simulation with open source tool, and here with low budget tools. So next, we are currently working on open source tools here, and we take the approach from University of San Diego, California, for Open Road they're called. We are pretty far, and we take the open source PDK from IHB, which you can get from GitHub. So I think we finish and we make a first tape out of this by mid of this year at least, yeah. And then we have a toolkit which can use students at home, yeah. So this is our plan, and we are very close to get finished here, yeah. So conclusions. Chipyard. It's not easy to get it installed. You need some software experts, yeah, with for the installation, and there you need also some skills for Python and Makefiles to get it configured. But I think computer engineering student or engineering student can easily control it, yeah. We had a problem with Chipyard when we always get to the newest release of Chipyard, yeah, because there the tools do not really combine. So please do not upgrade to the newest release as soon as possible. Please try out before you upgrade, otherwise your whole system is no longer working. You have to then reinstall everything, yeah. And then we had some problems with Fertile, yeah. With respect to Chisel, it turned out to be very efficient for multi-core or many-core RISC-V architectures. So we have very good experience. It's very fast, yeah. However, we see the engineering problem. Chisel, the perspective and working with Chisel is not engineering oriented. So there you basically have to think like a software engineer and not like a Verilog engineer. Yeah, this is a real problem, and but we are getting closer for it for the education. Yeah. So this concludes my talk, and I hope you understood most of it, though you don't have any Verilog skills, and probably learned today what a FPGA is, or I'm not really sure. Yeah. Okay, thank you very much for the